We will talk of Six Sigma, as we have been talking that Six Sigma is something where we will require your understanding of some statistical tools. So what we will do today is we will start up the discussion depending upon how much uh, time do we take in understanding this. We will try to look at whether we can finish it today or not. So, in order to do that, let us start our discussion on Six Sigma. So, first of all, what I will do is I will try to discuss with you the basics of Six Sigma, and then we can talk of the actual mathematical part of it, and then we can talk of how is actually it is executed. So straight away, let me take you to the PowerPoint so that we can look at what is Six Sigma and how we can actually look at the other things. So Six Sigma, if you would look at, uh, is basically a statistical control technique which invariably talks of uh, increasing the accuracy of our processes. Very important to note here is that it is about processes, it controls the processes, it ensures that the processes which are running for us are actually under control. Six Sigma, if you would look at right down to its history, you would realize that the companies like Motorola, Honeywell, and General Electric, they were the companies who have first used Six Sigma approach. Just to give you a sense of it, though we will also try to do it, just to give you a sense of it, that the accuracy level that we are talking of in Six Sigma is 1 in 1 million, is 4 in 1 million. So which means if 10 lakh units you are talking of, say, production, you can expect the four problems, four problems, productions. So what we are invariably talking about here is that Six Sigma increases the chance of accuracy, but very important to note that what if Six Sigma is increasing our chances of accuracy, but at the same time it is not guaranteeing us absolutely defect free process, because in 1 million you have 4 defects. So this is also a defect thing. So why I am telling you this is because maybe achieving the absolute perfection is something which is unattainable. So when we talk of Six Sigma as to be a very robust technique which lets us understand that it would increase our accuracy, but at the same time it is also not the thing which actually takes us to the zero defect. And hence you can relate it to the continuous improvement, which yesterday we were talking about. The idea was to keep on improving, because there is always some scope of improvement. See, if you have attained perfection, so there is no more room for improvement. So you are never achieving a process which is 100% accurate. So there is always some scope of improvement, and hence the concept of Deming cycle that we have done yesterday, hence the concept of continuous improvement. So all those things actually are resting into this very basic thing, that you have to think of your process to be always improvable, right? So we also look at in productions and operations Six Sigma as to be a program which lowers your cost, which saves your time, and which improves the customer satisfaction. These are actually outputs of implementation of Six Sigma. This is how actually we kind of look at it. To have Six Sigma model implemented, to have Six Sigma thing in place, what we can think of is we have to have a project or purpose or scope, and I will tell you why these things are important. Because see, Six Sigma, you must understand that Six Sigma is always a process oriented activity. So which means you apply Six Sigma for a process. uh, just to keep you posted about the example that we will be doing in this, so that you are online. that it has a very specific purpose. Now what we will do as an example case in understanding Six Sigma is, now suppose you think of a company who is producing say chips, right? So for example Lay's, for example any other company who is producing chips. Now for example the weight, I am representing weight by W. They expect the weight of this packet to be, say suppose 20 grams, right? So 20 grams is something that they would want that each of the packets which is coming out of the assembly line of Lay's should have 20 grams of weight. So this is a hypothetical case that I have taken. Now you would expect everyone to be having the same weight. You now take this weight as a mechanism on which you can think of having Six Sigma applied, and the purpose of this Six Sigma model can be that if at all my production cycle, my assembly line which is producing these packets of Lay's of chips, if the weight of these packets is larger than 20 grams, or if it is less than 20 grams, then this piece has to be rejected. In other words, we are applying Six Sigma onto weight. So there is always, so weight is a process here. That is what I am trying to tell you. This is very important. You can have multiple processes also. So you will have the Six Sigma implemented on weight now. So every packet should have 20 grams of weight. Now, which means if we are applying Six Sigma on weight for this chips packet, we are expecting that that 4 in a million, so 4 in 1 million, 1 million I am representing with 1m, there would be 4 packets out of the million packets that this company is producing which might have weight other than 20 grams, right? So which means we are ensuring the process where the weight of these packets would not go beyond a certain limit of 20 grams. Obviously we will talk a lot about in detail about this 20 gram thing also, but here it is important to understand that Six Sigma is meant to give a check to the processes. You can do it to weight, you can do it to anything else also. So that way, in this context, we are going to discuss Six Sigma here. These were the companies who have first started implementing Six Sigma into their production cycles, production procedures. We were talking of Six Sigma as to be a place, as to be a mechanism, as to be a process where we say that 4 in 1 million, 4 in 1 million would be actually default products, right? 4 in 1 million would be default products. This is how we are actually kind of looking at it. So Sandeep, when you say go on previous slide, this is the first slide. I think you would remember it. This is the first slide that I am starting today. So now this Six Sigma is meant to lower the cost, save time, and improve customer satisfaction. Now what I was trying to explain to you is that Six Sigma is always for a specific purpose, right? This is what I was trying to tell you. Now what this purpose was, though I have explained it, but maybe because of this connectivity thing we have skipped it, so let me very quickly start it again. Suppose we are talking of a company who is producing these packets, suppose say Lay's packets, this is the example that I was giving, and suppose we are talking of weight, I am writing weight by W. So suppose the company wants that each packet has to have 20 grams of weight. So hypothetical situation I am taking. So each packet has to weigh 20 grams. So if I am producing 1 lakh packets in a day, if I am producing 10,000 packets in a day, we want all those packets to be having 20 grams of weight. So this is what I want. Now you can apply Six Sigma on the weight. This is the purpose that I was trying to explain to you, right? So the Six Sigma is always process specific. On what process you would like to implement Six Sigma. So here when we are saying that every packet has to be 20 grams of weight. So this is the weight process on which we will try to have the Six Sigma implemented, right? 20 grams. So if suppose it so happens that out of so many packets that you're producing onto your assembly line, Suppose if the weight goes up, then the 20 gram, and if it suppose comes down, then the 20 grams, then this packet has to be kind of, not go into the final stage where it is dispatched. It has to be stopped there only, right? So this is how we are talking of the Six Sigma being implemented for a specific purpose, and the purpose here is that the weight has to be equal. So there is something in marketing we have already talked about, the conformity. Conformity means that every packet has to be of the same size, exact 20 grams of weight. So what do we essentially do is we implement Six Sigma. We can implement Six Sigma at multiple times. So suppose the weight here we have taken an example. Similarly, we can have it done onto something else also. So very important to keep in mind that Six Sigma is always context specific. It always is for a specific purpose. To be able to do that, to be able to identify that if there are some packets which are larger than 20 grams or lower than 20 grams, we have to know this, and we will only come to know this when we collect the data, right? So this is why the second stage is collection of data, and then from the data collected we analyze it, right? So what I was telling you is that because this Six Sigma includes analysis of data, so that is why we need statistics. And that is what I have been telling you, that we need to have a basic understanding of the normal distribution, the statistics, the central tendency, and this is what essentially we would require when we will try to look at this. And then on the basis of this analysis, we would either modify or we will either redesign our assembly line, and then we kind of control it also. So controlling would mean, as you would have been hearing this term every now and then, the controlling means to get back the things on the line that they were expected to be on. So this is the controlling thing. Now if you would remember the first initial level discussions that we have had on operations management and productions and operation management, I have talked to you about Walter. Walter was the man who has contributed a lot to the quality. When we were discussing that the history of operations management, so just to give you a very quick recall on those things, we have talked about those muskets being produced at mass level. We were talking about Henry Ford, who was talking of this assembly line. In those continuation slides, we have already talked about Thompson, Walter Thompson, perhaps, if I am not wrong. And that gentleman was actually someone who has contributed a lot to the quality management. And this gentleman has talked about the controls also. He has talked about some charts, right? And this is how the Six Sigma entire model works on. It first specify its purpose. To get and to reach to that purpose, we collect data, we analyze that data, and then we, on the basis of this analysis, we control our processes. This is how we go about it. Now, in order to understand this, we will talk of some stats here, we will talk of some maths here. So I will try my level best to explain it to you, but it would require for sure further reading, right? Six Sigma works on the basis of something which is called as statistical process control. Now, we have already talked about Six Sigma model. We have talked about the process, that it is always implemented onto the process. And we control this process, so which means if the process is going out of control, we get it back using Six Sigma. How does it happen? We will try to understand. And we use statistics in this. So what is the difference between statistics and maths? Applied maths is statistics. So when you are using mathematical procedures, theories, theorems to solve some problems, we actually treat that branch of mathematics as statistics. So statistical process control is the use of statistics, or is the use of maths to control our processes, right? So here the weight thing we were talking about, we are trying to control the process through which we are generating the packets of certain weight, right, of certain volume. So that is why it is defined that the statistical process control is application of statistical technique to control the processes, and that is what I have explained here using the title of the slide also. In that, we will be talking of something called as acceptance sampling. Acceptance sampling is we actually would either accept or accept the lot. Now you would be hearing this, that if there is a faulty product which is reported by the consumers, then the companies would say that the entire lot has been recalled, right? So from that lot, from where the sample was taken, that lot is either accepted or is either rejected, right? So if the sample taken from a lot A is actually in the statistical process control, so the statistical process control says that no, it is okay, then the entire thing is accepted. If it is in problem, then the entire thing might be rejected, depending upon the sensitivity of the company. Now, to understand this, we have to understand the concept of sampling distribution, right? I do not know whether you would recall it from your class of research methodology, but sampling distribution is actually something which is heavily used while we are trying to determine sample size in research methodology, if you would recall and if you would remember, right? So in Six Sigma also we are using the concept of sampling distribution, right? And we would talk of how and what this concept is. So I'm trying to explain this as follows. Now, to understand the sampling distribution, what it is, let us hypothetically think of a class, because you are students, so let's take example of class only. Hypothetically, let us see that, or let us imagine that your class has 38 students, right? There is a class which has total number of 38 students, so this is 38 here. Now, suppose if I ask you that how many samples of size 5 can I make out of the class of 38? So, if my question is okay to you, what I'm trying to essentially understand from you is, out of a class where the total number of students are 38, how many possible samples can I draw of size 5? So which means I'm making out of these 38 students, I'm picking up 5 people, so this is my one sample. I'm picking another 5 people, this is my sample number 2. I'm picking another 5 people, this is my sample number 3. I'm picking another 5 people, this is my sample number 4. So the question is, how many samples can I take or can I draw of size 5 out of the class of 38? You can type it into the chat box if it is making sense to you, or if you know how we can do that, because this is the maths which we need to understand in this. If we are skipping it, then it is going to be a problem for us, right? So just to put this in perspective, let me take you to the Excel sheet, and in Excel sheet let me try to explain this like this, right? So let me increase the size of font. What I'm trying to ask you is, suppose there is a class where there are 4 students. So there is a class where there are, so students are 4. Class, there is a class, right? So this is class 1. Now suppose I take a sample size which is 2, right? 2 is the size of my sample. Now the question is, how many samples can I make of size 2, right? Of size 2, how many samples can I make? Suppose these 4 students are A, B, C and D, right? So how many possible samples can I make? So Lalit Mohan says 7. So let us see AB, let us see AC, let us see AD, right? Let us see BC, let us see BD, and we can talk of CD, right? 1, 2, 3, 4, 5, 6. So I would have skipped something. If you would recall out of your maths understanding, you would invariably realize that we can talk of here combinations and permutations. There used to be these two terms in your mathematics class, if you would remember out of your school time, right? So here indirectly what I am trying to ask from you is, how many possible combinations can you make out of your class of 38, and if the sample size is 5. So the thing here is, suppose this is the total number of population size, this is the sample size. How can we do this is, in Excel we can very easily do this. I'm typing equal to, and I'm typing combine, right? So you can see this combine function. So I'm typing combine. So number is 4 and number chosen is 2. This is my sample size. So this is my another number. So it is 6. So 6 possible combinations we can make out of this. So this is possible combinations, right? So 6 sizes I can make, right? So Sandeep says 12. Uh, I think we would get back to that because maybe both these entries are wrong. It is not 12. So I will come to this now. So there is also something called as permutation. We do not use permutation here because permutation takes care of order also. So what the permutation would do is, in combination we are treating A, B as one sample, but in combinations AB is one sample and BA is no different than AB. This is how we look at it. In combinations, AB is equal to BA, but permutation treats AB different than BA. So the order is important. So because here when we are talking in statistics, order is not important for us, so we are going to combination. So now, let us make this class size 38, which is our case, and let us make sample size as 5, right? Let us make sample size as 5. So let us come to this formula, and instead of 2, let us select this, right? And let us come to this number. So this is how much? 5,01,942. This thing should amaze you because of obvious reasons, because these are the total number of samples. 5,01,942. These are the possible number of samples you can make out of a class of 38 for a sample size of 5. So in other words, what we are saying, 5,01,942 possible samples could be drawn from a population size of 38 for a sample whose size is 5. So these many samples I can draw out of the class of 38, right? I hope this should be clear to you, right? Now the same thing, if we would take it here, if we can now go to our PowerPoint slide, we were here only, and we can very easily say that the number is 5,01,942. These many samples we can draw out of this class of 5. So you remember that formula of NC5. So I have done nothing. N is the total population size. So for us it was 38. NC R, so R is my sample size, so R I have put as 5, and this has given me 5,01,942, right? So the samples I can draw are many samples, huge samples. So you just now are talking of a size of 38. Imagine if this size is large, it is going to be a very big number, right? Now understand it carefully. Out of this 5 lakh, more than 5 lakh possible samples that I could draw, let me choose any one sample, right? Out of this 38 class, now this is representative of the 38 students. These are 38 students, right? So out of these 38 students, the possible sample possible are more than 5 lakh, right? This is how we have looked at it. So more than 5 lakh. So it is 5 lakh plus sample I can draw out of this population of size 5. So what I am doing now, I am choosing up any one sample out of these 5,01,982, right? So I have chosen these 5 people here. What I do, hypothetically, let me assume these people, or suppose we were talking of weight. We've taken the example of weight here. So let us take the weight example here. So what I do, that these people are A1, A2, A3, A4 or A5, or you take it as X1, X2, X3, X4 and X5, right? So if I can take weight of these 5 people individually, right, A1, uh, and I take an average of these 5 weights and I call this average as A1, right? So what I've done is, this is the class of 38 students. I chose any one sample out of the 5 lakh samples which are possible, and then I observe, I calculate the weight of all these 5 students separately, and then I take a mean of the weights of these 5 people, and I'm calling this mean weight as A1. Is that clear? you can type it into chat box. Similarly, uh, I take sample number 2 and I take their average, and I take sample number 3, I take their average, I take sample number 4, I take their average, and what I am calling this average as A2, A3, A4, and likewise I can go and keep on doing this till I reach to the last sample possible, which is A 5 lakh 1942, and I make these means represented with the alphabet A. I say A1, A2, A3, A4, A5, A6, AN, A 5 lakh 1942, right? Very important to understand. Now, out of this 38 students class, 5 population, 5 sample size, the number of possible combinations were more than 5 lakh. For all these possible combinations, I took the mean, and now instead of individual observations, I am talking of means. So A1, A2, A3, A4 are means. If I can understand this carefully, if I draw the relative frequency distribution of A1, A2, AN to A 5 lakh whatever, now then that is called a sampling distribution, right? If I, again, let me reiterate it, if I can do a frequency distribution of A1, A2, AN, A5 lakh whatever, then that would be called a sampling distribution. Now the question is, what is frequency distribution? It is not a very difficult question to answer. Frequency, as you know, it is the number of times the observation is repeated. So suppose this is A1, this is A2, this is A3, this is AN, and then on this side you will have A5 like whatever. So there would be suppose many samples who would be giving means equal to each other, right? And because many samples are giving the same mean, so the repetition of mean would come larger in between, right? And hence the middle curve is the highest thing, middle graph is the highest, right? So this relative frequency distribution is sampling distribution. Very important here. If we would look at this sampling distribution, right, then we must be able to say here, and this is a theorem in mathematics also, it is a proven thing, that if we further take the mean of A1, A2, A3, A4, AN, and A5 lakh 1942, it will be an absolute mean height of the class. Like it will be absolute mean height of the class. So do not confuse it, but understand it. A population, a sample, how many possible combinations can you make? You take all those combinations one by one. You take the means of those combinations, call those means as A1, A2, A3, A4, AN, and you further take the mean of A1, A2, A3, A4, AN. Whatever will be the value of this mean, that would be the absolute mean height of your class. Now let me further put it into perspective. You could have done the same thing. You could have got the mean height of the class by simply going to the 38 students separately, or mean weight of the class by going to 38 students separately. You go to student number 1, you ask him what is your weight. You go to student number 2, you ask him what is your weight. You go to student number 3, you weighs his weight, and 4 and 5 and 6, and go to 38, and then you say that I have taken the mean of all the 38 observations that I have had, and this is the mean height of, or the mean weight of this class, whatever you are measuring. If you are measuring height, let it be height. If you are measuring weight, let it be weight, right? Now the same value of mean can also be derived using sampling distribution. So simple, if you would have done x1 plus x2 plus x3 and till x38, right, x38, because there are 38 students, and if you divided that by 38, this would be the mean of the entire class. So I am calling it as A of class. So AC I am calling it. This AC is absolutely equal to this mean also. This is what we are trying to understand, right? So this is an important thing. So sampling distribution, what we are trying to understand here is sampling distribution would have means as its observations, but not as the actual data that you have. So actual data was the weight of one individual student, but sampling distribution does not have weight of one individual student. It has mean weight of samples now. So A1 is not simple students weight. A1 is mean of 5 students taken together. And then you say that the difference between this average and this average is that AC is the average of actual observations, but this average that you're getting by following the sample distribution is average of means, but these both are equal to each other. This is property number one. Now, so what we have looked at is that the population mean, suppose we call it as P, is equal to the mean of sampling distribution. So I am saying sampling distribution mean, suppose I am calling it as S1, right? So these two are equal. Now the next question is, will the variation will the variation will also be equal of these two things? Variation, I am saying VAR. Will the variation will also be equal for what? For the class taken simply 38 students and the sampling distribution SD, right? Will this variation will also be equal? What I am trying to tell you is, and hence I was telling you to read this concept, that you can easily calculate the variation of any data, as you can calculate very easily the mean of any data. Similarly, you can calculate the variation in the data also. And how you can do that is, there is a formula. Standard deviation has a formula that you subtract the value, suppose x1, from the mean, which is uh, x bar, and you make it into parentheses and you add it, then you do x2 minus x bar. So you keep on doing this, and you then divide it by the square root of n or something like this, and you get a standard deviation value, so which is very easy to calculate if you know the formula. So you can easily calculate the standard deviation for this 38 students, right? Very easily you can do that. You can also calculate standard deviation of A1, A2, A3, A4, AN, A5, right? So in other words, what I am asking is that suppose you are using 38 students separately, taken their weight, and you have taken the standard deviation of class, suppose I am saying SDC, whatever it has come up, will it be equal to the standard deviation of sampling distribution? So I am saying SD. This SD is standard deviation, this SD is sampling distribution. This SD is standard deviation, this C represents class. Will it also be equal? Means are equal. We have looked at that the means are equal. Mean of the population, which is class, is equal to the mean of sampling distribution. But will it be true for variation also, which is the standard deviation also? The answer is no. It is not equal, right? It would require a little stat knowledge to understand this and to make sense of this. Why is it so? Because if you would look at the formula of standard deviation, which I have written here also, standard deviation is inversely proportional to the n, which is sample size. It is inversely proportional to n. And so, which means larger the n, larger the size of sample, lesser the standard deviation, right? Right? You can let me know if you are understanding it. Type something in chat box so that I know that it is making sense to you. Standard deviation formula is inversely proportional to the size of sample, which is n. Larger the n, lesser the SD, lesser the standard deviation, right? So which then means that in this class of 38 students, the n is only 38. But in case of sampling distribution, the n is how much? 5,01,942, right? So this is the difference between the n of the two things. Since the number of samples in sampling distribution are Very thank you, Joydeep, for the answer. Since the number of observations in sampling distribution are in lakhs, they are 5 lakh 1942. So the standard deviation of sampling distribution would always be less than the standard deviation of population, right? So this thing, which is the class, would always be high than this thing, which is standard deviation of this standard deviation of sampling distribution. Thank you, Lalit Mohan. You got your response. So, what is the relationship? The relationship is if I represent sigma. I hope you would know what is sigma. Sigma is a letter which represents the size of which represents the variation. So sigma represents the variation, right? Sigma SD, which is the sigma standard deviation of sampling distribution, shares a relationship with the standard deviation of population in this way. It is like this, right? This is the relationship between the standard deviation of sampling distribution and standard deviation of population. So the simple sigma represents the standard deviation of population. This sigma SD represents the standard deviation of sample distribution, and it is like this. So n decides how much is the difference between these two. Okay, so this is how we are looking at it now. Then let us look at it like this. Uh, this thing that you're looking at it here, you look at it like this. I'm drawing it here. The sampling distribution, if you would look at, would always be a normal distribution. It would follow the shape of a normal distribution always. This is what has been found out. And why it is so? Look at this another theorem. It is theorem which is coming from maths. Central limit theorem. You would have heard about it. What this theorem says, that regardless of the distribution of population is the 30th students, right? This is the population. This is population. The distribution of means of samples is standard deviation, is sampling distribution. Sorry, sampling distribution, because sampling distribution is means of samples. Would tend to follow a normal curve as the size of sample increases. Why? Because you take any sample, any population, you do this homework in your home at your own ease. In sampling distribution, the number of samples would always be on higher side in comparison to the number of observations into the population, right? To make sense of this, let me take you to Excel sheet again, and let me try to explain this to you. So I'm going into new sheet, and let me increase it. Suppose this is the population size, right? This is the sample size, and this is the combination, right? So suppose the population size is 10. I'm intentionally taking the population size as to be a smaller number so that you can understand it. And let me take the sample size as 0. We will increase it, right? So I'm dragging it down. This also I am dragging down. Will it fill? Yes. Then I'm further taking it down. So what I'm doing is I'm increasing the size of sample. So let me increase it till 10, right? So let me make this also 10, and then let us do this formula of combination. Combine this comma this. So this is NCR that I have run, and this is 1, and you send it down. Now see what is happening. Very important, and this tells you a very super important story. As you would increase the size of sample, so here the sample size was 0, here the sample size is 1, here the sample size is 2, here the sample size is 3, here it is 4, here it is 5. As the sample size is increasing, the number of combinations are also increasing. So it was 1, 10, 45, 120, 210, 252, right? So the combinations would increase, and there will be a point till that point the combinations would increase, and after that point it would start to decrease as a mirror image. So what I mean by the mirror image is, so 252, you come to this side it is 210, you go to that side it is also 210, 120 it is 120 there, it is 45 it is 45 there, it is 10 here and it is 10 there, so it is 1 here, it is 1 here, so it is a mirror image of this. So this is the central point, right? This is central point. Now, so there is a lesson into this. Lesson into this is the howsoever small or big is your population size, but as the sample size increases, the combinations also increases. So even for a population size of 10 and a sample size of 2, the possible combinations are say 45. Our case is when we have 38 here and 5 here, right? So in our case, we have population size as 38 and sample size as 5, right? So as we will increase the size of sample 5 to, so now you see this is sample size is 5, which is half of the population size. So at a point when the sample size is half of your population size, so which is half of 38 is what? So half of 38, whatever is that number, 19. Till 19 size of population, 19 sample size, the number of combinations would increase and thereafter it would decrease, right? So just to make sense of this, here look at this, this is 5 and you do the combination story here. The combination story is combine NCR and it is 5 lakh this time. You increase this, right? I am filling this series and let it be same, right? So send this formula down and you see it is increasing, right? So you keep on increasing this size till 19. So I'm intentionally doing this so that I can show you that thing, and you keep on doing this here and further send this formula down. So you see for 19 it is maximum and then it has started decreasing. So this 33 is equal to this 28 is equal to this. So for any population size till half of its number, it makes sense. Beyond that it start decreasing, so the combinations would start decreasing. So here the story that I'm trying to tell you is a very important thing, that as the sample size increases, then the combinations also increases for any specific population size. In our case, here our sample population size is 38, sample size is 5. So if we increase the sample size by 5, it will further increase. But for, as a rule, as a token of rule, you must know it and you must remember that the sampling distribution size would always be larger than the population size. So population size was 38, but our sampling distribution size is 5 lakh above for a sample size of 5, right? So then this central limit theorem says that for increased sample size, the distribution would be normal distribution. So our case was that we have 5 lakh 1942. So the distribution that we are talking here is, we have already talked this, the distribution we are talking here is, it is going to be normal distribution by central limit theorem. So I am saying central C limit L theorem T. By following central limit theorem, this distribution is normal distribution. Which distribution? Sampling distribution. So sampling distribution is normal distribution by central limit theorem, right? So now what we are saying is that whatever distribution we have got of the means, because these A1, A2 are means, this is actually a normal distribution. Now this is what I have been telling you time and again, that you need to know what is normal distribution to understand Six Sigma. Now normal distribution has some properties, and these properties are that mean sits right in the middle of this. So if I can make a normal distribution to you, it looks like this, and this right into the middle sits the mean, right? It is mean. This side and this side are equal, are mirror image if it is a normal distribution, right? So this portion is equal to this portion. This is another thing, right? So the standard deviation of the normal distribution is 1. It is 1 unit, right? These are the properties. So if barring the other properties, if we take only these two, these both things are now applicable to sampling distribution, because sampling distribution is a normal distribution. So we would implement everything that was true for normal distribution. Now we will say this is true for sampling distribution also, because sampling distribution is a normal distribution, right? So now let us try to make sense of this. And you don't go to this theorem. This theorem talks about how many observations are onto the left side and to the right side of the of any type of distribution. Do not confuse it. Now come to the normal distribution. Now this is very important thing. Very important thing. If you understood this, you would understood the essence and the basics of Six Sigma. A normal distribution would have a mean sitting right into the middle of it. Remember now, this is something very super death important. Understand this, and from here we will start using the term Six Sigma, right? Now look at, in the middle of this curve we have a value of 0, right? We have a value of 0, whereas we were saying that the middle is mean. So are we saying the mean is 0? No, we are not saying mean is 0. Here in this normal distribution, the value 0, 1, 2, 3 represents a statistic which is Z statistic, and this is what written here also, Z scores. Z statistic has a formula, and the formula runs like this: x minus x bar divided by sigma. This is the formula for Z, right? This is the formula for Z. Now understand it carefully. If our sampling distribution, which we have just drawn for our population 38 and of sample size of 5, is following normal distribution, so the properties of normal distribution are equally applicable onto the sampling distribution. For sampling normal distribution, the Z is calculated like this. Now see, what is this? Look at the numerator, x minus x bar. X bar is mean. This is mean. This is observation. Because, understand this, because the central value in normal distribution is mean value. Central value in the normal distribution is mean. That is what I was telling you in the previous slide. If it is mean, so what is Z doing? This is frequency distribution only, so frequency would mean it is going to be observation. Now suppose if our weight case we have the mean 20, right? If the mean is 20, so in the middle the value that you are having is 20 only, so 20 minus 20, it becomes 0. 0 divided by anything, it becomes 0. So if it is 1, we say it is 0, and hence the value is 0 here. So this value 0, 1, 2, 3 and 4 is the value of Z. You see the Z is written here for normal distribution, right? Very important property also, for a value of Z equal to plus minus 1, because this is a normal distribution, it is a mirror image, so right hand side is equal to the left hand side. Whatever is onto the right hand side would always be into the left hand side also. So for a value of Z which is equal to 1, the number of observations within this region, so this region which I am highlighted with the violet color, this region would have 68% of the total observations. Another property, right? Remember this, when value of Z is 2, when value of Z is plus minus 2, then the number of observations that you have within this area, the green thing which is highlighted, are 95%, right? Are 95%. And when you are talking of Z value as 3, which is here, the number of observations which are under the curve for these value of z is 99.73. Okay. Now look at this like this. If I if you are understanding it, you would realize for our case of sampling distribution, if I can take you to the Excel again, in our case of sampling distribution, this is our case, right? We are talking of, let me drag it little downside. We are talking of z value, right? We are talking of area under the curve, right? And we are talking of number of samples. I will tell you what is this. Z value when it is 1, we say area under the curve are 68%. I am just writing like this. For Z value 2, we have 95.45%. This is also 68.27%. Percent has come twice, so I will delete one. This 3 is 99.73%. Right, this is 3. Okay. Now our sampling distribution had a total samples as 5,01,947, whatever number. So this area would have this multiplied by 68%, right? So now I am sending this down. I am also sending this down. No, it has to be formula, not this. And 4. Okay, so this is what? This is this 68%. Now this value has to be 95%, because we have 95% samples here. This is 99%, so this value is to be 99%. Now look at this. Understand this very carefully. Very important thing. For a value of z which is 3, the total number of samples which are under this curve now are 4,96,927, which means out of 5 lakh plus samples, look at this very carefully, out of 5 lakh plus samples, 4,96,927 samples are within this area of curve, right? Now I am taking you back to the slideshow to make you understand what are we discussing here. So for this value of z, which is 3, we have 4 lakh almost 96,927 observations out of 5 lakh, right? Out of 5 lakh plus, right? Now, so whatever samples that you choose from this class of 38, the possible number of samples are 5 lakh plus. The samples which would give you a mean value for z value plus minus 3 would be these many. So you would end up in choosing these samples out of many cases. Now, just to make one more important observation, and then we talk of Six Sigma from here. Let me tell you very important thing. Z, this is the formula for Z, right? I'm taking the leap from this formula, and now can I explain Z in terms of variation? In terms of variation, this is my question, right? In terms of variation, or when I say variation, I am essentially saying sigma, which is the measure of standard deviation. Understand this very important. What the numerator of Z is doing? It is measuring the difference of an observation from the actual mean. Can I say Z is measuring what? Z is measuring, and important is you can write it down also somewhere and then you can understand it later on. If you understand it now, fantastic. Z actually tells you how many standard deviations away you are from actual mean. This is what Z tells you, right? Because look at this, Z is having sigma, which is standard deviations, right? So if it is having sigma in denominator, then you treat this. So you can write z as difference, which is d, because this d is x minus x bar. I am writing as difference multiplied by 1 divided by sigma. This is how I can write it. So how many standard deviations away you are from actual mean is nothing but it is z. So when you say z value as 3, that means you are 3 standard deviations away from the mean, right? 3 standard deviations away from the mean. Now, in continuation to this, can we get a value of z for sampling distribution? Now this is value of z for normal population. So let us do it for sample distribution. So z for sample distribution, which is SD, it will be, this is important, x here is x bar. Why x bar? Because we have written x bar as a1 here, right? So I am writing a1. Why? Because in sampling distribution our observations are means, they are not simple uh, observations. That is what I have told you. So minus, this will be x double bar, instead of x bar it will be x double bar. And why x double bar? Because you remember this slide, uh, the mean of a1, a2, a3, an is equal to the mean height of the class, which is x double bar, right? So the observations here are mean, so that is why in z I have written x bar minus x double bar, which is this value, which is mean of these means, and this is what I have written here, divided by sigma sd, standard deviation of sampling distribution. You would recall this sigma sd is not equal to the standard deviation of population, right? This is where we have done this. I hope you would remember. If I can tell you this, you look at this thing now. So let me highlight this so that you are not confused. Let me highlight this. Okay, let me change the color of my pen. This is what I am saying. This is right. So sigma sd is equal to sigma divided by root of n. So now I am putting this value into this value, right? So let me again change the color of my pen. Let me make it red. So this thing becomes x bar minus x double bar divided by sigma, and this is further divided by root of n. This is your SD, ZSD. This is your ZSD, right? So this is what the ZSD is for sampling distribution. So you can always calculate a value of Z for sampling distribution by putting in these values, right? Now, since Z we are looking at as how many standard deviations away we are from actual mean, look at this value for when Z is equal to 3 minus 3. So when Z is equal to plus minus 3, why? Because on to left hand side it will be minus 3, on to right hand side it will be plus 3, plus minus 3. So the number of observations are 99.73. If you would convert this 99.73 into a whole number, you would see it is 4 in 1 million. This is what we are talking in 6 sigma. Since Z is how many standard deviations away you are from actual mean, when Z value is 3, So when z value is 3, which is plus 3 minus 3, so this portion is plus 3 portion, this portion this portion is minus 3 portion. So here z is 3, here z is 3, so 3 plus 3 becomes 6. And as this is z, and as z is how many standard deviations away you are from mean, and standard deviation is sigma, so we say 3 plus 3, and that is how it becomes 6 sigma, which we write as 6 sigma, right? This is why it is called as 6 sigma, 6 sigma, right? 6 sigma, and it will give you guarantee of 99.73 accuracy. 99.73 accuracy would mean, let me change the pen color, 99.73 accuracy would mean that you are getting only 4 defects in 1 million, right? Now let me very quickly rewind it for you so that it doesn't create problem to you. We have started from sampling distribution. We have looked at sampling distribution as frequency distribution of means of a specific sample size for a specific population size. Population size example that we took is 38, and the sample size we took it is 5. And we have taken each sample individually and we have plotted, so that you can follow. Let me show the slides to you so that it is like easy for you to follow up. This is where we have started from. How many possible combinations we can make is 5,01,942. Then I have taken the first sample, I have taken the mean of this first sample, I have called it as A1. Similarly for A2, similarly for third sample, fourth sample, and similarly I have done it for all the possible samples that were there till A5,01,942. When I have taken these means and when I have done the sampling frequency distribution of these, it gave me this shape. And this shape, by following this logic that A1, A2, A3, A4, if you will further take the means of it, it would be the mean height, it would be the mean of the population. It would be equal to the mean of population. Then we are going to central limit theorem. Central limit theorem says as the sample size increases, so the distribution tends to follow normal distribution. In our sampling distribution, sample size was huge. It was more than 5 lakh. So for any case, our distribution would be normal distribution, and hence we say here that sampling distribution is actually normal distribution, and therefore the properties of normal distribution can be mirrored for sampling distribution also. And when it can be mirrored for sampling distribution, then we have talked about that the mean of normal distribution sits right into the middle of it. Both the sides of it are the mirror image of each other. The standard deviation of the normal distribution is 1. And the mean of the sampling distribution is equal to the mean of the population, and the standard deviation is not equal to the standard deviation of sampling distribution. What is the logic behind this? We have already looked at. And then we have actually looked at normal distribution, we have looked at Z, we have looked at the formula of Z. That formula of Z is then taken into the sampling distribution, and then we have talked about this 0, 1, 2 being the value of Z, and then we have talked about the 3 Z's onto the right hand side, 3 Z's onto the left hand side, so in total it becomes 6 Z. Z is what? Z is nothing. Z is how many standard deviations away we are from actual mean, and hence we are talking of 6 standard deviations in total, and standard deviations are represented by sigma, which is a symbol, and hence we talk of 6 sigma. And what will it give you? For a value of Z as 3 and 3, for this value of Z, the number of the accuracy is 9973, which is 99.73. So we are that much accurate in 6 sigma, and that actually comes out to be value of 4 in 1 million. So this is how we have actually looked at 6 sigma and the concept of 6 sigma. So this is basic opening vignette about 6 sigma, how theory, what theory works behind it, how does it happen, and if you can kind of look at this again and again because it is getting recorded, I think you will get the sense of it. Now we can with this understanding behind, we can start doing Six Sigma implementation using some dummy data, and then we can try to look at it. So till now, if you have any questions, why do we call it a Six Sigma and all that, you can just let me know. Any questions, Lalit, Joydeep, Sandeep, Nitu, uh, Abhishek was also there. So any questions out of from anyone whosoever is attending now till this point? Has it made sense to you? You can just very quickly let me know, and then we can start the second part of it, which is looking at it from the perspective of operations management, and we will try to look at it how is actually this implemented. Right? Okay, so if some questions come, I will take those questions as and when they come. Now, so what we have looked at till now is this point, this statistical techniques to control the processes. Right? This is what we have actually looked at, and what is the statistical technique and what is the logic behind this technique. That is what we have looked at. Now, very important thing. Uh, there is something which is called as causes of variation, because you see we are talking of Six Sigma, right? We are talking of Six Sigma, and sigma is nothing but variation, right? Sigma is nothing variation. Okay, Sandeep, it is helpful. Best online class till date. Oh, thank you so much. You can anytime come to me for the query, Sandeep. I would always try to solve it up. So now we are building up this. We are building up this understanding of Six Sigma to you, and then we are looking at the dummy data, and we are looking at how actually it is implemented in the companies. So now, since the name of this technique is Six Sigma, right? And Sigma is variation only. So what we are trying to do, we are talking of variation. So that is why we are talking of causes of variation into our process. So when we have taken this example of 20 grams weight of any company, whosoever is producing these chips. So we are interested. So we were talking of this 20 grams, right? We were talking of 20 grams. So we are interested in looking at variation in these 20 grams. Is it going up or it is going down? This is what we are interested in. And this is variation, right? This is the variation. Now, very important to note, Six Sigma theory divides this variation into two types. One is common, one is specific. Right? Common variation is also called as natural variation, and specific variation is also called as assignable variation. Now, let us spend little time onto this. They say that for any process to run, there are some variations which we cannot control. There would be some variation. Now, suppose if we are talking of 20 grams of weight, you might have a packet which is giving you weight of 20.002 grams. It is not exactly 20 grams, but it is 20.002 grams. So this is also variation. In fact, if you would go statistically by maths, it is still a variation. Now, this variation, can you control this? Howsoever great machines you have in place, howsoever great labor you have in place, whatsoever good environment and platform you make available to the people, but you cannot control this much of variation. There is a type of variation which is uncontrollable, and this type of variation is called as common variation, which is natural variation. So you cannot control this variation, it is bound to happen. But there are some variations which are specific, assignable, as the word itself suggests, assignable, which means you can assign to something. Assign to something means this variation. Now suppose if this comes out to be 21 grams, right? If suppose this comes out to be 21 grams, now there is this variation of 1 gram which is quite high. Now can you assign this 1 gram more weight to anything? And if yes, you are talking of this assignable variation. So which means you might talk of the wear and tear of machine, which is very much controllable. You can talk of the fatigue into your staff, which is very much controllable. You make the shift time accordingly, you change the shift time accordingly. That is what you can do. So what the Six Sigma does is, Six Sigma basically looks at this 20 grams of the thing, and then it assigns the limits, the upper limits and the lower limits. These limits are for variations, right? So variations means what? Uh, Suppose the upper limit is 0.10 gram. Suppose this is the limit, right? So which means 20.10 grams and 19.90 grams. So this is like 20.10 grams, right? 10 and 19.90 grams. So these are the upper limit, this is upper limit, this is lower limit. So if I can take you to this curve, this was the curve, this was the curve, and this is the middle point of it. So here the z value was -3, z value is -3. Here z value is this side z value is +3, and hence it is 6 sigma. So this upper limit is this, which is 20.10. This lower limit is 19.10. So if any packet which is being produced is within this variation of 19.90 grams and say 20.10 grams, it is acceptable in the Six Sigma, right? So it is allowing this packet to go to the dispatch center. But if the weight of this packet increases and it is more than 20.10 grams, and if it is less than 19.90 grams, this is not a natural variation, right? This is not a natural variation. If this is the case, this is a assignable variation. This is this variation. So that is actually highlighted by Six Sigma. So in other words, what we are saying, understand it very carefully. For Six Sigma, 99.73% accuracy we are talking about. So which means that Six Sigma will guarantee up to the extent of 99.73% that the packets that are going out of this factory, if this factory is following Six Sigma, would have a weight between these two range. There would be only 4 packets out of 1 million, out of 10 lakhs, which might have weight which is larger than 20.10 grams and less than 19.90 grams. There would be only 4 packets in 1 million because you are having Six Sigma implemented, right? It still has errors, but the errors value is so, because you were talking of 99.73% accuracy, in Six Sigma 99.73%, right? 73%. So how much error you are allowing? You are allowing 0.27%, right? This much of error is actually allowed, right? So this becomes 4 out of 1 million. So 4 packets might have a weight which is beyond 20.10 and less than 19.90. Otherwise, all the packets would have weights between these two limits. And these anything which is beyond this limit is called as assignable variation. Anything which is within this is called as natural variation, right? How do you do that? You do that using control charts. And this helps separates the two. Which two? We are talking of these two variations, right? So very important thing, because we have already done sampling distribution, so with this thing in place, we create the sampling distribution. The Six Sigma thing creates the sampling distribution analysis, and then it actually generates the upper limit and lower limit, and then it sees whether a packet is going within this limit or it is going beyond this limit. And it is if it is beyond this limit, then it is said that no, it is not into the control, right? That is why the control charts gives the limit, right? The logic behind this is that the natural variations, the variations which are like 0.002 grams, they behave like a constant system because they would be there. They are not changeable, they are not controllable, they would be there, right? They would behave as a constant system. And if you would look at these observations, you will see that this variation can be plotted like this. This variation will be normal distribution, right? And with time, if you can plot this, with time, suppose if this is the time, with time, if you would plot this, you will keep on getting this normal distribution. If the shape of this normal distribution changes, that means you have assignable variables. To make sense of this, we have to do 2 tasks. First is we need to ensure that the process is operating under control. Second is, if there are any assignable variations, we need to eliminate it. So if it is because of the machine, we need to check it up, we need to control it up. If it is because of something else, because it is assignable, so we can assign it to something, so we can also control it, right? Now this is what I have been telling you. Suppose the Lay's factory or any other factory which is making chips. Now these chips are going down the assembly line. It is a fully automated system, and then this is packing automatically. So this is unmanned assembly line. You can think of this a fully automated line, and then the weights of these are then kind of calculated, and then these weights are looked at through Six Sigma, and if it is okay, only then they are allowed to go through, or if they are not, then they are kind of curtailed back. Now this is a very important slide in the sense, before looking at this slide, let me try to explain this to you by taking you to the Excel sheet again, right? I'll come again to the Excel. Now, suppose this factory that we were looking at, which is producing these chips packets, and they want these chips packets to be of the specific weight, of the specific weight size. Now suppose this factory starts at 9 a.m. in the morning, and on the first hour, suppose between 9 to 10 a.m., you pick up a packet randomly, which is generated by this factory, which is made by this factory, and you weight this packet. And suppose this weight is 17 grams, first hour, right? In first hour, you take these 9 samples, right? So second sample that you have taken in the first hour is weighing 13 grams. Third sample, 16 grams. Fourth sample, 18 grams. Fifth sample, 17 grams. Sixth sample, 16 grams. Seventh sample, 15 grams. Eighth sample, 17. Equally 9 sample. Not 9 sample, 9th packet. These are 9 packets that you are taking in hour number 1. And for each packet you have got the weight done. You remember this is what we were talking about, 38, and so population size, this is population pop, this is sample size SAM, it was for 8 for us. Here we have taken sample size is 9, right? This is what we are doing. Our population size is too much. How many packets are being generated in 1 hour, that is our population size. But our sample here is 9. Right, so this is the 9, 1, 2, 3, 4, 5, 6, 9. As we have taken the mean of x1, x2, x3, x4, x5, x6, x7, x8, and something. In our PPT, we were talking of 5 samples, so we were taking mean of x1, x2, x3, x4, and x5, and we've called it as A1. Right, we've called it as A1. Similarly, we are calling it as sample 1. Here. Our sample size is 9. These are the 9 samples. As for first student we were having weight calculated, similarly for first packet we are having weight calculated. So what we do now, we have to calculate A1. Here A1 will be mean of all these things taken together. So how can I do this? Is very easy, average of all these things taken together, right? And the average has come out to be 16.11. So what we are discussing here is, as in the PPT, first 5 students, their weight was taken, and that mean of their weight was called as A1. Similarly here, instead of 5, 9 samples are taken in hour number 1, and their weights are taken, and the mean of their weights is taken. This is equivalent to A1, right? Then hour number 2, 9 samples further taken, and their mean is taken, that becomes A2. Then hour number 3, 9 samples taken, their mean is taken, that becomes A3. Then you keep on taking these samples till you have a larger sample available to you. Here, for the sake of understanding, we are taking say 12 samples, right? We are taking 12 samples, right? So number of samples we have taken are 12, sample size is 9, and population standard deviation is 1. Because we are talking of normal distribution, and in normal distribution the standard deviation is 1, right? Now sample number 1 mean we have just calculated 16.1. So similarly, suppose for sample number 2 we have 16.8, which is mean. Suppose we have sample number 3, which is 15.5. Suppose sample number suppose sample number 4 we have 16.5. For sample number 5 we have 16.5, 16.4 for sample number 6, 15.2 for sample number 7, and accordingly we have this sample 12 samples and their means taken together. In PPT, analogically, so that we can understand that, we have formulated the frequency distribution of all these. A1, A2, A3, A4, frequency distribution of all those. That's what we have done. Here also what we are doing, we will do the frequency distribution of all those. And then when the sample is quite large, we will have a distribution coming up, and that distribution will be normal distribution. If that is a normal distribution, then all those properties that we have looked at are then applied, and then we look at how do we decide what is going to be our upper control limit, what is going to be our lower control limit. So suppose here we take the desired weight of these packets as 16 grams hypothetically. So I am writing desired is this is what we want. So this is 16 suppose, and I am saying okay to it, right? So the desired has come out to be 16, right? Now then what we have to do is, we have to calculate LCL and we have to calculate UCL. LCL is what? Lower control limit, and UCL is upper control limit, right? And we know, we have already looked at the formula of it, using which we can calculate it, right? Now let us go back to that formula so that we do not get confused. This formula was here I am writing this formula, Z equal to X bar minus X double bar divided by sigma SD, right? Sigma SD. This is what we are doing. Now we are interested in calculating this. So solving this formula, what we will get is X double bar. Sorry, X bar. It is not X double bar. I am crossing it down. X bar equal to X double bar, which is the mean of population, plus Z multiplied by sigma SD, right? This is our formula. Now this sigma SD, you can also write it as equal to X double bar plus Z. Sigma SD, we have already seen this relationship, sigma divided by root of n, right? Now further solving it, X double bar is the desired size, you see, desired limit. So desired, there in the Excel sheet we were calling it as 16. We want every packet to weigh 16 grams. A while ago we have looked at it. Then plus. Now value of Z is what? You look, we are only taking plus sign. So if you would recall this normal curve, so this is the center, and when we go towards this side of it, we call it plus, and when we go this side of it, we call it minus. So since this is plus, so from here the value of Z was 0, here the value of Z was 3 in 6 sigma. So because we are talking of plus, we will put the value of Z as 3 sigma here. Sigma value is 1, normal distribution, divided by square root of n. N is how much? 9 in our example. So I am putting 9 here, right? So you solve it. So square root of 9 becomes 3. 3 divided by 3 becomes 1. So 16 plus 1. So it becomes 17, right? So it becomes 17, right? So this is your UCL, upper control limit, because it is plus. Similarly, you can solve it for minus. So for minus, I am coming to this side. So you can talk of minus as 16 minus 3 multiplied by 1 divided by square root of n, and square root of n means it is 9, and it becomes 15, right? It becomes 15. So this is z in, this is z, this is z in this side, this is z in this side, and this is z in this side, so this side, right? So plus minus, so z3 this side, z3 this side, so 6 sigma. So you have UCL and LCL, so that is what I have depicted, UCL and LCL here, right? So this is what you want, and desired is represented with blue, and this is your sample means, right? And this is the hours. Hour number one, you have the sample mean, whatever you plot it here, right? So you then look at these distributions. You see, this is how it might look to you, and these are outside the limits. These means are outside the limits because these are your means, right? The yellow, the blue, and this thing. So when look at this very carefully, I am bringing these down. So with time, if these distributions are not changing, if it is equal, then we say that yes, it is actually good. We are making sense of it, and it is something which is called as in statistical control. This is called as in statistical control because these limits are not going outside UCL and LCL. That there is this variation which actually needs to be looked at two levels. So the first level is wherein you are looking at whether the spread is okay. So if the spread is okay, then you can kind of go ahead with it. If the spread is not okay, then you also look at it as to be a problem thing, right? So then this is how I was trying to explain to you that this spread that I'm talking about, this spread is increasing, and this spread essentially is talking about something which is like uh, if it is increasing, it is also a problem. And why it is a problem is because you were talking of this upper control limit and lower control limit like this, and when you were talking of these limits, it is actually going out of these limits, and when it is going out of these limits, then also it is a problem, right? So this is how we actually look at Six Sigma. We calculate the lower control limit, we calculate the upper control limit, and then we try to see whether the distribution is within this or if it is outside of this. If it is within this and if it is outside of this, that actually lets us know whether we are actually in control or in not control. Just to put that in perspective, have a look at this slide. This slide is actually letting us know the three scenarios that can potentially occur. So the first scenario is when we have this as our one limit, this as our another limit, and our all these things. So because I need to change the color of pen because this is already in blue. So if this is the case, then we say that we are into statistical control with natural causes, so there is no problem, right? We can have this scenario also where the spread is more. So though we are into control because the variation is not changing, variation is constant, but we are actually spreading outside of our limits, right? So we would say it is a problem. And if this is the thing, then we are out of control and we are into the assignable causes. So what do we look at is this: we actually look at our this distribution with time, and this time lets us know that if the variation changing. So when you will go into any organization which is implementing Six Sigma, you would invariably look at a monitor, and that monitor would keep on displaying this thing, this distribution along with time. So with time, this distribution should not change, right? So if this is the case, we are into problem, right? It is a super problem, so that is assignable causes, right? So we actually have to look at this type of variations all the time. With time, it should not change. If we are actually looking at this, then it is a problem. So I remember last time when we visited industry, there we remember looking at a computer system, a monitor. That monitor was flashing these things, this variation continuously, and that was just letting us know that everything is in control. If this variation changes, now suppose if with time it becomes this, it is a problem. So we know that this is not a natural cause. This is a assignable cause that we are looking at, right? So I think this is how we can look at it. And when I was right, thank you very much.